Hello. In today's lesson, we'll be going over how to solve inequalities and express domain and range through interval notation. So first, we're going to go over how to write interval notation. So hopefully we've already learned set notation right here, which dictates the set of numbers in a region using inequality signs. But there's another way to write out sets of numbers, which is interval notation. And as you can see here, if an interval is finite, which means that it's ending on both sides, we would simply put the endpoints right here. And you might notice that we have both brackets and parentheses. So these indicate whether or not the endpoints listed are included in the set of numbers. So the rule is that if the endpoint is included, we'll use brackets, and if the endpoint is not included, we'll just use parentheses instead. So another type of interval that we might encounter is an infinite interval, or one that goes on forever and ever. What we'll notice here is that we always use parentheses for positive or negative infinity. This is because infinity isn't an actual number, it's just a concept. So we can approach infinity, but we'll never actually reach it, so we will just use parentheses. Lastly, there are some rules for if there are multiple intervals. When we have two or more intervals, we will join them together using this U, which stands for union. And there's also an upside down U, which stands for interactions between intervals, but we won't need to use that for these kinds of problems. So one situation where interval notation is really useful is for expressing domain and range of functions. We can think of the domain and range as sets of numbers, and we remember that we can express sets of numbers through interval notation. So for example, right here in this function, we can see that the domain starts at 0, inclusive, and ends at 5, not inclusive. So we'll write it out like this. And for the range, we can see that it starts out at -3. It's touching -3, and it reaches 6, but it never actually touches 6. So we'll write it out like that. And for the domain of range for functions that go on forever, we can, of course, use the infinite interval and write out the infinity with the parentheses. Okay, so let's move on to solving inequalities. If we get an inequality like this with two variables, there are only a limited number of things that we can write out about it. So we could find the domain and range, or we could try and graph it. In this video, I'll just quickly go over some tips here. So what I like to do first is think of this as an equality, just y equals x plus 3. This will dictate where I draw my line or draw my graph first. And depending on whether or not this inequality is inclusive, I'll decide whether to use a solid line or a dotted line. In this case, this is not inclusive, so I'll use a dotted line. Next, a trick here is that if I have the y isolated here and all the x terms here, I can decide which side to shade based on the inequality. So since y is greater than, I like to think of it as being above, so we'll shade in the area above. We'll see another example of this later on in the video. So if we want to solve an inequality for just one variable like this, we'll have an inequality like this. And now this number line is what it would look like if we graphed it out, but let's try to solve it algebraically first. So what we'll do is we'll subtract 3 from both sides, and then we'll just flip it to make it look nicer. And that's basically our solution. But this is in set notation, and we know that we can convert this to interval notation, like so. And if we check back on our line graph, we can see that the solutions match up nicely. Now that one was pretty simple since it was just a linear graph, but what if we have a polynomial? We'll start off simple with this second degree polynomial or quadratic here. Again, we have all the x's on one side, all the x terms here, and the y isolated here. So I will just graph it out as if it were equal, and I will use a solid line because I see that it's inclusive here. It's less than or equal to. And since the y here is less than, I will shade in the area below the graph. So now that we have this inequality with just x, we'll just be solving for x. And corresponding with that, we have this kind of wonky looking line graph. So let's see how we can get this graph algebraically. First, I'll flip the inequality. This isn't necessary, it just helps me recognize that I'm going to be solving this quadratic for zeros. So we could either plug this into the quadratic equation, or we could try to factor this quadratic to get the zeros. I will just do the quadratic equation here. And we can just assume that this is equal to find the zeros for now. And we find that our zeros are 0 and 2. Now this helps us divide out our line graph into different intervals, like so. And what we can do is we can test different points in these intervals in our original inequality to see if it satisfies the inequality. So for example, for this first interval, we could use -10. In this interval, we could use 1. And in this interval, we could use 10. And if we plug in numbers from these intervals, we'll find out that this first interval works, this interval does not, and this last interval works. And how we'll write out this solution, we could write it out in set notation, or we could write it out in interval notation, like so. From -infinity to 0 inclusive, since it's inclusive here, and from 2 to infinity inclusive again, since it's inclusive. And if we check back with our line graph here, we can see that that matches up. So now hopefully you've noticed that both of those previous problems involved graphs that crossed the x-axis. But for graphs that don't cross, there is a more simple shortcut. So the solution, if the graph doesn't cross, will always be either all real numbers or no solution at all. And for all real numbers, we'll express it like this with -infinity and positive infinity as our interval with the parentheses, of course. And for no solution, we will write it out as this O with a dash through it to show that there's no intervals to satisfy the inequality, or no solution. So using these new concepts, please try out the practice sheets that will be linked below in the description, and check your answers on the solution sheet, which will also be there. Thank you for watching.